everyone. I'm Yuan Tian from Pittsburgh University. I'm glad to present our work, SQLucid grounded natural language database queries with interactive explanations. This work is in collaboration with Professor Jonathan Comerfield, Professor Toby Jiajun and Professor Tian Zhang. In the era of big data, there is a growing demand for querying databases. Traditionally, it requires an expert user to write a formal language such as SQL to query a database. To democratize data processing, recent advances in machine learning enables non-expert users to query data through natural language interfaces. These interfaces are powered by text-to-SQL model, which automatically translate a natural language question to a SQL query. While these models are very convenient, they are not perfect. Currently, the best model have an error rate of at least 10% on Spider and 27% on BERT, which are two widely used text-to-SQL benchmarks. In reality, this value can be even higher, and it is not acceptable in high-stakes domains such as finance and healthcare because they cause severe consequences. As a result, users don't trust the model. To bridge this gap, recent work has been focused on developing interactive approaches. These approaches include human in the loop and aim for two objectives. First, they aim to explain system decision to users in an understandable way, which helps users increase their trust and detect potential errors. Secondly, they aim to incorporate user feedback during or after the explanation, the generation, to remove ambiguity in natural language questions and allow the user to fix detected errors. For example, MISP, DIY, and SQLucid are three representative interactive approaches. MISP incorporates user feedback through multiple choice questions. DIY provides a multimodal explanation and allows users to give feedback through drop-down menus. SQLucid explains a generative query as a visual graph. Unfortunately, a recent study has shown these approaches are don't work really well. Compared to manual editing, these approaches doesn't make a lot of difference in performance improvement. In their study, participants complained that it is hard to understand the generative query and provide feedback. More specifically, their explanations are limited and the feedback mechanisms are constrained. To bridge this gap, we draw inspirations from grounding theory in communication. Grounding theory is a social psychology concept. It points out that during a conversation, people should establish mutual understanding through the common ground. Common ground is a set of shared knowledge, beliefs, and assumptions. They are used to ensure messages interpreted correctly between each other. We present SQLucid, grounding natural language database queries with interactive explanations. It has three key features: editable step-by-step explanation, visual correspondence, and the intermediate query results. According to grounding theory, when a human user communicates to an intelligent agent, they should establish mutual understanding based on a common ground. In our approach, we design this common ground in the form of interactive explanations, and the explanation is editable and step-by-step. These explanations describe the query behavior generated by the agent. It is understandable by both human and agent. The human and agent can communicate with each other by directly editing these explanations and collaboratively refine the query together. To generate the explanation, we leverage a grammar-based approach. In short, the idea is that given a SQL query, we first parse the SQL query into a SQL component and translate each component into a natural language component. And finally, we rearrange this component to form a step-by-step explanation. So the grammar-based approach is fast and reliable. In practice, we found users may still confused about the step-by-step natural language explanations due to some naming conventions in databases. For example, a column name could be an abbreviation, which doesn't make sense to end users. To address this issue, we enrich the textual explanation with visual correspondence feature. SQLucid detects columns, tables, and values in the explanation. When users hover their mouse over this keyword, the related data automatically pop up and highlighted and show on the side. This feature helps users to mentally relate the textual explanations to concrete data, and users can use this feature to efficiently navigate through the database. Here is an example. Flight is a table and origin is a column. When user hovers the mouse over them, the corresponding data are highlighted and displayed on the side. SQLucid further enrich the explanation by integrating the calculation of intermediate query results. When user clicks a certain step, SQLucid synthesizes a temporary query, execute it, and return an intermediate result. This feature helps users to understand the actual functionality of each step. In this example, there are 3 steps in total. When user clicks the first step, it retrieves all the records in the flight table. And then when user clicks the second and third step, the temporary query and the intermediate query results are updated. Through our highly interactive explanations, if user detect any errors, they can freely edit the explanation to give feedback. As shown in our UI, user can add a new step, deleting existing step, and they can also edit existing step through free-form natural language. After user edits these explanations, SQLucid regenerates the query. And user can also check edit history and undo or redo some edits anytime. To enable the user to edit the explanations in free-form language, we develop a text-to-clause model, which takes a description of a certain step as an input and outputs a SQL component. This model is modified from a transformer-based text-to-SQL model. It was fine-tuned on synthetic data produced by our grammar-based approach, and it achieves a 90% exact match accuracy. To evaluate the usability and the effectiveness of SQLucid, we conducted 2 user studies. In the first user study, we compared SQLucid with other interactive approaches. In the second user study, we investigated the effectiveness of individual features in SQLucid through a Bayesian study. User study 1, we compare our baselines are MISP and DIY, which are 2 representative interactive SQL generation approach. We recruited 30 participants with various levels of expertise in SQL. We asked them to try to complete the SQL generation tasks within as many as possible within 10 minutes using different tools. Our results shows SQLucid significantly outperform other approaches. Using SQLucid help users to correct more tasks correctly with higher accuracy. We also investigate the influence of user expertise in SQL generation. We found that SQLucid consistently improves performance across different user expertise. We also investigate the influence of task difficulties. And we found SQLucid consistently improve performance across different task difficulties. And particularly, they are especially effective for harder tasks. Through our final survey, we found SQLucid significantly improve user confidence and reduce their cognitive load. In the second user study, we create three baselines by disabling intermediate query result feature and the visual correspondence feature. We recruit 8 participants and ask them to complete the same tasks as in user study 1. And we found both the intermediate query result feature and the visual correspondence features contribute to performance improvement. And through our final survey, we found that both of these features contribute to improving user confidence and reducing their cognitive load. Based on our findings, we list 4 major design implications. First, it is beneficial to establish a common ground for mutual understanding. And second, it is beneficial to implement free-form feedback mechanism to improve performance. And third, it is beneficial to use text decomposition to reduce text complexity and isolate errors. And lastly, it is beneficial to use visual correspondence for navigation in data-intensive applications. In conclusion, we introduced SQLucid, an interactive database query system. SQLucid helps users understand generative query and freely fix errors. SQLucid significantly improves natural language query performance with less user cognitive load and higher confidence. Thank you so much for listening. Feel free to scan the QR code for more details in our paper, code, and demo.
Hi, really interesting talk. I want to ask a question about the text to SQL part. How complex is the SQL being generated? And how do you handle the nested SQL? Because you know that there are lots of like query like nested select or some like that kind of complex query. Can your system handle this? Because I see all the explanations are step by step and in sequential way. So yeah, that's my question. Thank you.
Okay, that's for your question. I think your question is about nested SQL. In this example, it's just an example for demonstration. Our system can recursively handle nested SQL query. For example, this is actually a subquery in SQL. If there is another SQL query and union together with this query, our interface will show 2 subqueries, and we provide some guidance explanation, such as in the first query, and then show this, and in the second query, and show another one. And then we also explain the relationship between 2 subqueries. That other question is not shown in the paper, in the UI here, but it is shown in our website. And we have a demo website online. You can try it if you like.
So it's shown on the website of the.
Yeah, we have a if you scan the QR code, it's a GitHub link, and there is a online demo. It's a.
Thank you.
Thank you. That's for your question.